are, and you've also done the reading guide, which is a really good recap, right? So you have a great background knowledge from that respect as well. So, Levi's group, somebody tell me a property of gas that you just know.
Boils long.
Tell me a property of gases.
They fill up any container.
Okay, so they fill their space. That's one property. Savina's group of two. Okay, so they fill their space is one. What's another property of a gas? It's compressible, right? We can compress gas. Compressible, right? Jinkies area? What's another property of gas? Say again? Say again? Okay, so they spread. So they're, I'm going to say low attractions for each other. So meaning they spread out, right? They diffuse. Chloe? Y'all spread? I'll come right back to you. Levi, just have to bit over here. What's up?
Elastic collisions.
Okay, so they collide. They not only collide with each other, but they collide with the containers. And in that, they generally have elastic collisions. And what does elastic mean? No loss of energy. They can collide, and hopefully no one loses energy. The energy is hopefully stored. Yeah?
The molecules are in random motion.
Okay, so they randomly move around. Close group. So that's a pretty good list there. What are they generally consisting of? What's their composition of? So they are molecules, but molecules consist of nonmetals and nonmetals, right? Nonmetals and nonmetals, so they're covalent compounds. All right, so we can go on and on. So what you'll notice is that I will eventually start to reference the Lewis-Dot models. Like, so for example, carbon dioxide, the Lewis-Dot model, back in the day, you learned that it looks like this: C double bond, O, dot dot, O dot dot, like this. Do you remember drawing some Lewis-Dot models like this? Maybe. Yes, shake your heads or something. You're like, oh, maybe, okay. So we're going to reference how they're covalently bound together, and then also their polarity in a little bit. Okay, so these guys right here, these have a special name. These are called manometers, and I think how these are on your note sheet in front of you. And so what we have to deal with is the fact that gases cause pressure. Well, gases are pretty much the only substances. We have liquids, solids, and gases in plasma. But gases are what can cause pressure because of that whole collision aspect that they are able to do. So they are able to collide with the size of the container. Levi, do you need something? Okay, I gave you a type tester. I have one more here if you want. Oh, sorry. Okay, so if you this manometer looks very, very different than a barometer. And so the barometer is something that we're going to be utilizing in the lab next week. It's actually called a eudiometer, E-U-D-iometer. And so it's just an up-down piece of glass that's actually kind of like a graduated cylinder because there's graduations on it. So what you can imagine is that there's pressure everywhere. Where's the pressure right now in the room? Where's it coming from? What's around us? Okay, so the air around us is the pressure of the atmosphere. The pressure of the atmosphere is pushing on us, and our bodies are just so strong they're withstanding it. We're not being crushed and imploding or anything, right? So the atmosphere is always present, meaning it's always able to push around gases that we create in the lab. So we create gases through chemical reactions. So we also can create it through like evaporation processes. So there's always a combination of gases in the room. So we have to identify them as P atmosphere and P gas. So these inside of the manometers that I have here, we're going to call those P gas, because P means pressure, and the little subscript of gas right here means I'm talking about the pressure of that gas. It could be carbon dioxide, it could be oxygen, it could be hydrogen, it could be many things. But then we also have P, the atmosphere, PATM, that's outside, that's pushing on our gas of interest. Now this is a closed-in manometer, so there's nothing like the pressure of the gas and the pressure of the atmosphere really don't interact because it's closed off. So what can happen is the gas particles fill their space, and they fill all the space within it, like we said before, for properties of gas. Well, in the open-end manometers, two situations, or actually three situations can exist. The pressure of the gas and the pressure of the atmosphere can be equal. The pressure of the gas and the atmosphere can be unequal, with respect that the atmosphere can be stronger, meaning higher pressure, or the gas can be higher pressure. So generally the way we describe that, we show that, is that we have some mercury, and I'm going to draw this as a solid blue here. We're going to have some mercury in our manometer tube. So this mercury is something that we always reference in terms of pressure. Where have you heard mercury with pressure before? Thermometer, that's temperature though, not pressure, right? Where have you heard of mercury in reference to pressure? The unit of pressure is what? MHD, right? Millimeters of mercury. It's literally and I don't have an actual true picture of a barometer up here. The barometer has mercury in it, and then what they do is they take a ruler and they hold it up and they go, oh, it's 70 millimeters of mercury today. Because it's actually a reference to pressure, because the mercury particles are so close together and they're so dense, it actually equates to that. We'll talk about that a little bit more later. So in terms of pressure being described by mercury, what we do is we assume the pressure of this gas in here is pushing on the mercury right here. So it's pushing on the mercury, and mercury is a fluid, it can move. And the pressure of the atmosphere is also pushing here. So the atmosphere is just kind of everywhere, right? And so it's pushing. So as you can tell, the mercury levels are equal. So what can you assume? Pressure gas, pressure atmosphere are equal. Pressure gas equals P atmosphere. So then what would this be if I drew my mercury levels changing? So let's say the mercury level goes up to here. What can you assume? Who's greater? Pressure of gas is greater than pressure of atmosphere. By how much? The height, the difference in heights between the two mercury levels, right? So what we have is we would really utilize a ruler, and we would say, okay, from here to here, there's a difference in height of mercury, millimeters of mercury, and we call that difference in height delta H, and that was what we would add to one of the pressures. So here, I want you guys to derive your own pressure summation. So is it P gas plus delta H equals P atmosphere, or pressure of atmosphere plus delta H is equal to P gas? Why atmosphere? Because it's lesser, right? So this is lesser. So what we have to do is we add the delta H to that, and that gives us the pressure of the gas, because the pressure of the gas should be the greater one, as you guys described from our picture. Question? It's actually, we don't do half the delta H because it's pushing that much more. And so it doesn't matter if I'm up this way, it's the distance that this has traveled.
But like as that, like you're on the left side goes down, that's going up as much on the right side. So like if like it pushed the down, this side's going up. So
but because they're both moving in the same direction, it's additive. I see what you're saying, because you want to, but it's already added here and added here. So it's actually already negated that halfway thing you're talking about. Because it's moving the same direction. I know what you're saying. It's a good point. Okay, so we got this. We could do this. Now, what would you assume the pressure of the atmosphere would have to be recorded in to appropriately do this? What units would we need that pressure of the atmosphere to be in? To use that formula, because the delta H is referring to millimeters of mercury, it's a height. We have to have that in millimeters of mercury as well. So we need to have consistent units. So speaking of the units, go ahead and tell me what the units are that are kind of every type of way we could express pressure in. We already know millimeters of mercury. What else? Atmospheres. Remember, atmosphere is ATM, that does not mean atom. What else? Kilopascals. And, okay, PSI. Two more. Torr, Torr. And bar. Did anybody see bar in their readings last night? BAR, bar. Okay, that's okay. So let's talk about the ones that we know the equivalencies of, and you actually get some of these on your reference sheet. So 1 atmosphere is equal to how many millimeters of mercury? 760 millimeters of mercury. Okay, those are two that we'll use a lot. There's one more equivalency. One more equivalency that we use a lot with kilopascals. Anybody? Thank you. 101.3 kilopascals. Those are the ones we use most common, so those ones we'll stick with. So that's why I have you looking at, you can use your reference sheet, you can use your active reading guide, you guys have all the information in front of you. So we're talking about pressure, we're talking about converting between pressures. You would use dimensional analysis to convert between these. You got me? We good? Okay. What about standard temperature and pressure? Somebody tell me what standard temperature and pressure is. 273 Kelvin, which is how many degrees Celsius? 0 degrees Celsius. So what's the conversion between those? So Celsius plus 273 would give us Kelvin. And then what about pressure? These up here, right? So all the ones we just listed, those equivalencies are our standard pressure. So if I say anything's at SCP, you will be always given those 2 data points, but I'm not actually saying the data points, right? I'm saying SCP, but you know that 2 data points are given to you. Okay, so the importance of that is sometimes we're going to talk about ideal gases, sometimes we're going to talk about realistic gases or real gases. And so they act a little differently under different conditions. So we'll be describing the conditions quite a bit. Now in gases, some people did the simulation yesterday. Others of you guys will jump on the simulation as you can. But you're going to be referencing a lot of comparisons between variables. There are a number of variables that are included in this unit. So before I want to move on to the other variables, I'm just going to highlight pressure a little bit more. And so you guys, you don't have this picture on your chart, but you can draw it yourself if you wish. What happens is we're going to start to deal with how does water play into our pressure. We don't have millimeters of water though, right, in our pressure units. We have millimeters of mercury. So we're going to talk about the conversion between that shortly. But remember, pressure is everywhere. Atmospheric pressure is everywhere. So if I have, this is water in a beaker, and I have atmospheric pressure out here, atmospheric pressure is going to be pushing down on the water. Well, this water was actually previously, and this actually says mercury, I'm going to use my water example first. This is a eudiometer tube. Okay, so eudiometer tube, and let's say there's water in it. If I have water in it and I have a vacuum at the top, there's a little gas, or there's a space at the top. What happens to the water as the atmosphere pushes on the water? Where does it go? It goes up. There's only one place to go. It can't go down anymore. It's already, gravity's already pulling it down enough. So what happens is the water can move up and up and up and up and up, and this would cause this to raise up a certain height. That certain height difference is measured in height, meaning millimeters of mercury, if it were mercury, but we're going to actually talk about later how do I convert between millimeters of water and millimeters of mercury, because sometimes we need to account for that. So what can you assume? I can't really show you this on this picture here. Okay, so if I have a eudiometer and I have water here, and I have my eudiometer upside down, and I've created, so the pressure of the atmosphere is pushing down on the water itself. The water can move up, right? If I've created some gas, and the P of gas is up here, what if my P of gas has pushed all my, because originally the water was all throughout this tube, and let's say all the gas has pushed the water down to this level here. Well, the water is down here, and the pressure of the gas has pushed the water down to here. What can you now assume about the pressure of these two things? They actually are equal. Pressure of the gas pushes, the pressure of the atmosphere pushes, and they meet at the water line. That means they're equal. But what if the water line is beneath, the water inside the tube is beneath the water line. So let's say it's down here. The pressure of the gas is greater because it's pushing down. Then what if it was up here? Pressure of the atmosphere is doing more damage, right? It's pushing the water up, and it's opposing the gas, so the gas is being pushed up, so the pressure of the atmosphere is greater. So I'm just showing you like 5 different ways to see the same exact thing. Okay? Okay? Okay. So let's hit some of the actual equations for today. So these are the 4 main gas laws that you guys have already been exposed to. So you guys can actually fill this out on the chart as we go. That's what the simulation was meant to give you some idea of how the variables are related to each other. So Boyle's law, you have a little graph over here. I've already given you the axes as volume and pressure. So the 2 variables involved in Boyle's law are volume and pressure. And I will always do this in my honors class, so I gotta do it now. Everybody, did you bring your box of air today? Got your box of air. Whip it out. Okay, you got your box of air, you got a special volume. Increase the pressure on your box of air. Okay, what happened to the volume? It got smaller. So how are they related, directly or indirectly? Indirectly or inversely, right. Okay, so pressure and volume are indirectly proportional or inversely proportional. So what is the equation for Boyle's law? I'll start you off. P. You saw this in your reading. Let's go. P1, V1 equals P2, V2. Okay, so those variables are, right now, are the only things changing. So what variables are remaining constant? Temperature is constant, and moles, N is the moles, right, is remaining constant. So we're going to talk about when that's actually 100% true, but right now, this is what we know. So then, how would our graph look? Positive slope or negative slope? Negative slope, but truly it's actually a hyperbola. Maybe like this. That's a hyperbola, right? What is that? Gentle slope. Exponential decay graph. Okay, so maybe if I go up on the other side, that's a hyperbola. Parabola? What did I just say? Okay. I'm thinking hyperbole. Yeah. So I'm going to stop using my math terms. I'm pressing you guys today. We're going to talk with chemistry. I'll speak with what I'm comfortable with. So it has a gentle slope, and that's because truly the most linear part of the graph is like right here. This is supposed to be pretty linear. It's supposed to be a pretty linear indirect relationship because at high pressures, low volume, high pressure is where it's most linear, and then it actually starts to differ a little bit at lower pressures, because the lower the pressure, the more spread out the gas particles get, and so it distorts the relationship a little bit. All right, but let's keep talking about just the basics of the relationships. So Charles's law, anybody? Relationship? Okay, we'll start with the equation. So V1 over T1 equals V2 over T2. And what does T always have to be expressed in? Kelvin. You shall never, ever put a Celsius into your equations. You can always answer it in a Celsius. You can always have a question with Celsius, and you cannot put it into the equations because according to the kinetic molecular theory, temperature has to be related to speed in Kelvin. So the temperature must be in Kelvin. Okay, so what variables are here? Volume and temperature are directly related. And that's because if I have temperature, right? So specific temperature. If I increase the temperature, what happens to the particles? They move faster. Okay, so if I have my box, of air, and I've increased the temperature on them, they're moving faster. So what are they doing to the container walls? Well, hold on. What are they doing first? They're increasing the collisions in the container wall. What does that truly mean? What's actually happening? At that point, if the collisions increase, the pressure is really rapidly increasing. Are you allowed to increase pressure in Charles's law? That variable is not changing. So what do you do to alleviate that increase in pressure? You increase the volume to stop the pressure from increasing. Do you see how that domino effect occurs? We explained that. You should be able to explain it as well. So we just said constants are pressure and moles. Okay, so we're not changing the amount. But as I increase the temperature, to eliminate the chances of pressure increasing, I must expand the volume. So that's why it's a direct relationship. You got me? Okay, I'm trying not to move too fast, but a lot of this is background information. So how would this graph look? Direct positive correlation. Okay, so as temperature increases, volume increases. As volume increases, does temperature increase?
No.
Not that. So it's a correlation, not a causation, right? So that's why I have on the x-axis temperature, not volume, because temperature increases causes the volume increase, not vice versa. Okay, so think about why am I putting temperature on the x versus the y-axis? Okay, Avogadro's law. What two variables are involved here? Volume and moles. I know it's on my graph already. Okay, so in this case, I have, according to my graph, moles on the x, volume on the y. So just give me that relationship in like one sentence. Okay, so an increase in moles would cause an increase in volume, assuming what stays constant? Okay, so pressure and temperature. So the equation is, anybody? Say again? V, so you said V over N? You do N1 over V1 or V1 over N1, it actually works out. So V1, I'll stick with this one, V1 over N1 is equal to V2 over N2, or N1 over V1 is equal to N2 over V2. They both work out because they're positively correlated. So your graph does look like this. So what happens if I increase the number of moles in my box? First off, what happens? Why does the pressure increase? So more stuff means more collisions. More collisions means pressure increases. No, you can have pressure increasing because we said it must remain constant. So then what do you do to alleviate? You allow the volume to increase. Okay, so you need to be able to break down very, very baby steps on why are these staying constant So how do I make it stay constant? The pressure is going to start to increase, so you must allow for the volume to increase. So really, you're really specifying a lot about collisions. Okay, so that's Avogadro's law. What laws are we missing? Gay-Lussac's and ideal gas law. Okay, so let's talk about ideal first. So I do have a bit of information about some of the Boyle's law. I'm going to come back to this though, because I'd like to apply these more today than talk about some more of the very, very, very specifics. So I'm going to come right back here. Okay, first off, what the heck is an ideal gas? Well, not all gases at STP will necessarily be ideal, but a lot of ideal gases act ideal at STP. But what makes them ideal? It's how it should behave. How should it behave? What should it do? Say again? Okay, so some of it's related to this. What'd you say? Meaning they behave identically. They behave in a predictable pattern. So I'll say they have predictable behavior. And what's some of that predictable behavior, Alvin? Okay, elastic collisions. What else? Say again? Okay, so they're compressible. How do they cause pressure? How do gases cause pressure? Collisions with the container wall equal pressure. Random movements, meaning if you are randomly moving, do you have any attraction for another molecule? No. Okay. I know that that's ideal, but if I'm a water molecule, you know water's bent, you know that, right? Is it polar or non-polar? It is polar. What's another polar molecule going to do with another polar molecule? Because the polarity differences actually do attract. So if we have a water, let's just quickly draw this, and then another one, I can draw this straight, be lovely, H2O. What's happening between them? Don't say attraction, give me the specifics. Okay, so the positive side of the H, so the partial positives, attracting the partial negative oxygen. What's that attraction called? Hydrogen bonding. Okay, so that's real. That actually happens, right? But what are we assuming with an ideal gas? We're assuming it doesn't. And my example in honors game is always, all right, guys, think of your ideal girl or your ideal guy. You can think about that perfect human being, but it's unlikely that you will ever find the absolute perfect human being. My husband, man, he makes me coffee every day. But what's something I don't like about him? I don't know. He's perfect. No, he's not perfect. Nobody's perfect. But what you can think of is that we know these actually occur, right? We know it. But if we assume they don't occur, we get to use the ideal gas law, which is, by the way, what? Ideal gas law is PV equals nRT. If we assume ideal gases exist, they all act appropriately, they don't attract to each other, they collide with the container wall without any weird attractions, we get to use that. If we assume real gases exist, we have to use the real gas law, which has a lot more variables in it. So we use this so that we can have a predictable process for solving problems like this. And so we're going to talk about real gases when we talk about the kinetic molecular theory. That's why we're allowed to use the ideal gas law, because we do a lot of assuming. And that's okay for right now, but we want to assume forever. Okay, so what different laws come together to make the ideal gas law? Boyle's law, so I'm just going to put Boyle's. What else? Charles and... Say again? Avogadro. Okay, and that's what the three we just talked about. That's how we get all of our variables interrelated. So as you already know, PV equals nRT is our ideal gas law. What is the R? Give me, I know it's a constant, what is it? What's the common one we use? Say again? 821 atmospheres times liters per mole K. Please don't get lazy. You will write this out. My people who don't like to write word. I'm training you to be a good student. I'm training you to get your points. I'm training you to get your, 5 on the AP exam, which is May the 1st. Understand your processes, problem solving, the whole mix, right? So you've got to put your units, guys. If not, I can't actually figure out the heck you're doing. All right, so the ideal gas law, P must be, if we utilize the R constant, what should P always be recorded in? Atmospheres. What should volume always be recorded in? Liters. M, moles. R is R. And T, Kelvin. If you are implementing the R constant, you must have these variables here. If you don't have them, get them. Got it? Okay. So there's one more rule that you may have read a little bit about, but we've never actually used in class before. It's actually combining density and the ideal gas law. So you have this on your paper? Okay, cool. So what is density? What's just plain old density? Okay, so density is equal to mass over volume. We're going to derive our own density formula. So that's mass over volume, and the ideal gas law is PV equals nRT. What is the commonality? What's the common variable between them? Volume. Solve both of these for volume right now. So V is equal to say again? Mass divided by density. Okay, I'm just going to put D for density actually. And then V on the other side, V on this side is equal to nRT over P. Okay, since both of our V's have been solved for, what can we now do with both these equations? Yes, we can now, since the V is equal to V, we can set mass over density is equal to nRT over P. I'm going to need a little bit more space for this. Let me see what I can do here. Don't want to show you. There we go. Okay, so if mass over density is equal to nRT over P, how can I get molar mass? What are the units for molar mass again? Grams per mole, okay? Do you see grams per moles here?
Yeah.
Basically, right? Can you rearrange so we can get grams per mole on the same side? What do I need to do? So multiply them both by what? Density. So density is going to pull off the bottom and come over here, okay? And it's gone over here. Divide by moles on this side, and you get moles on this side, right? Okay, so I just rearranged that really quickly, but what we have here is mass, we have molar mass, grams over moles, is equal to dRT over P. The way that I always remember this is molar mass is equal to dirt over P. DRT, dirt over P. And I saw this online and it cracked me up. They call it the molar mass kitty litter box. Cats put dirt over their pee. Like kitty litter over pee. Ah, you guys are great today. Okay, so you need to know this formula. Molar mass is equal to dirt over P. DRT over P. Now, I didn't say this. What does the density of a gas have to be recorded as? Density is always mass per volume, right? What specific units do you think a gas should be? Yes, it actually has to be liters. So density is going to be grams per liter. Grams per liter. Only because gases, they're so spread out. They take up so much space. We generally refer to them as liters, not necessarily milliliters. Cool? Okay, so I think that's, let me make sure, I don't need to tell you anything else here. We're going to start applying some of these. Oh, no, I got one more thing. So, I have it down here too. Okay. So, partial pressures, Dalton's law. We have Dalton's law, and that's just a summation of partial pressures. So what we have, and this is just on your paper, equation is P total is equal to pressure of A plus pressure of B plus pressure of C, and so forth. It depends on how many different gases are present within your compound. Within your mixture. So if I'm talking about the atmosphere, I'm going to give you an example here. If I'm talking about the atmosphere, P atmosphere, what different gases would that consist of? You guys who did the worksheet yesterday can tell me. P of, how do I write nitrogen? N2 plus P of O2 plus P of argon plus P of CO2 plus P of trace gases. I was going to say water vapor, okay? And then maybe we can do trace, right? Depending on what else is present. That's my Slayer thing. So what you can see is definitely we have a lot of gases that could be involved. But a lot of times in our labs, most of the time in our labs we're collecting, how do we collect gas in the lab? I'll start with that. This was in your reading guide. Leave it.
Water displacement.
Water displacement, right? So if I have water present, naturally water is always doing what at the surface? Just a teeny bit, just a little bit evaporating, right? So if I have a pressure total from a lab perspective, it's usually, because we're collecting gas for water, it's usually a combination of two gases. What would they be? P gas, whatever gas we're creating. It might be oxygen, it might be CO2, it might be hydrogen, but that's always going to be also combined with P of water vapor. And this will be something you utilize in the lab a lot. Okay? So what constants are present if pressure is the only thing we're dealing with right now? Basically, what things would change pressure if I manipulated them? Okay, so volume's going to stay the same. What else? Temperature and amount, right? It's the only thing that's not there. So we can't change that because then that wouldn't be summative at that point. Okay, so the only thing that we really didn't do last year, because this is all basic review except for density of stuff from last year. This information here, I'm going to let you read it for a second because I want you to see that you've read over some of this already, and then we'll talk about it. I'll stop. And I'm going to scroll up just a tad. So mole fraction, which one of my people who yesterday who were here saw mole fractions had, did they have units? The mole fraction yesterday, did they have units in the worksheet? They did not, right? Because it was moles of a particular gas of interest, and you take that and you divide it by the total moles present. So moles of gas over moles total, despite the fact they're talking about different things, it's still moles per mole, and so moles per mole will cancel. So mole fractions are actually unitless quantities, very similar to a percent, but it's just a ratio. It's part over whole. So what we'll utilize is N, right? So moles of our specific identity of gas divided by our moles total, and the way we represent the mole fraction is with X. So if I have, for example, so I have it right here for you, but X, so mole fraction is what X means, of carbon dioxide. What I would do is, let's say let's just pick a number, there's 1 mole of carbon dioxide in our room, in our atmosphere, and we would divide that by all the moles of gas in our atmosphere. So 1 mole of CO2 plus 2 moles of nitrogen plus 3 moles of oxygen. I can keep going. It would be summative on the bottom. And so this is our mole fraction, and we express it with X. So since mole fraction is just a ratio, I can also always get partial pressure of a gas by implementing the mole ratio, which I don't even have it on the board yet. I have a mole ratio here, but I can utilize the mole ratio and the total pressure to find a partial pressure. So a partial pressure is just it's just one gas's pressure in a total sample. And mole fraction is just the moles of one gas in a total sample. So they're very similar. What's different about them? Mole fraction versus partial pressure. What sounds like it's different? Say again? Moles, so amount versus collisions or pressures. So, but obviously they're directly related because as you increase the moles, what should happen with pressure? It should also increase. So that's where we're comparing them because they are directly related. The ratios are directly related. It's really easy. So in this sense, and you guys have some of this in your reading guide, of course, write down if you need to. What you can do is, how do I calculate partial pressure from total pressure? You take total pressure, P total, and you multiply that by mole fraction, and I'm just going to use A of my example here. And so my mole fraction I calculated by taking moles of my gas of interest divided by my moles total. I can multiply these together and I can get partial pressure of A. That's it. So sometimes you're given partial pressure. Sometimes you are given mole fractions and a total pressure, and you must find your own partial pressure. I know you guys are sleepy. Give me something that I know you're okay. Crack a joke, smile, thank you, thumbs up. I'm going to leave that there for just a minute. That's one of the new things for this unit. And then, can anybody guesstimate here for me? Give me a good hypothesis. Why doesn't Dalton's law of partial pressures depend upon the identity? Thank you. Say again? Okay, so So that's a good point. So we're talking about temperature really, but kinetic energy is a relationship with temperature. So temperature is directly proportional, or kinetic energy is directly proportional to temperature in Kelvin. So if all the gases in that sample are at the same temperature, we're assuming they all have the same amount of kinetic energy. And so if they all have the same amount of kinetic energy when they collide, truly their collision should all be equivalent. So I can have carbon dioxide, which weighs 44 grams per mole, and I could have oxygen, which weighs 32 grams per mole, and technically those collisions are considered equivalent. Hence, the pressure doesn't change because what's pressure based on? Collision. So if you got a collision, you got a collision. They're kind of saying all collisions are equal. It doesn't matter who you are. And I will tell you on this free response, and you guys will have some free response practice actually this unit before the test. This free response, they do a lot of explanations of connecting the dots. So that's why I'm trying to really elaborate on some of these explanations now for you. So they'll ask you just to explain why something, they'll say, oh, the pressure increased. So the answer's there, but you have to say why. So you have to do a lot of explanations. I'll leave it there for one more second. All right, we're gonna do calculation in a second, so make sure you have the calculator out. I think that's what's next. Yes, mole fractions. We're doing really well. We still have like 35 minutes, so I'm hoping that we get to our actual process. So, you know how to get partial pressure, you know how to get mole fraction, and let's see what we can do here. Actually, I'm going to say to you guys free. You have 2 questions right now, 1 and 2. I'll start with 1. I'll give you guys a second to get started first, and then while you're doing that, I'm just going to ask for you to, I'm just going to go 2 people at a time to see if you can guys. So just have them open for me. So what are you guys doing first, number 1? You're finding what? Finding moles of what? Of both gases, okay. So make sure fluorine and helium. What is what you mean by fluorine though? Just making sure. What's the formula? F2, right? Diatomic. And helium is just helium, it's just He. Are in a container with total pressure. So I would always be writing down my givens, and I do believe that's the most important part to kind of start with. Total pressure is equal to 4.0 atmospheres. There's 19 grams of fluorine gas and 4 grams of helium gas. So we have our givens. Very first thing, Alvin said is go to moles. What's the molar mass of fluorine, Alvin? 38. So you guys can do that math in your head. I don't even know why I said flush your calculators. You don't need that. How many moles is this? 0.5. So it's half of the molar mass. So 0.5 moles of fluorine. And then helium weighs what? 2 grams, right? Or does it weigh 4 grams? 4 grams, sorry. So then we have 1 mole of helium. So this math is easy. Do not use your calculator. Let's try to practice our mental math, okay? So if you have both of your moles present, how do I get to partial pressure? Let's talk about the equation first and then we'll implement. What equation would you use to get to partial pressure? P total times what? The mole fraction of one of our samples equals partial pressure, right? So let's go ahead and find our wet first. Mole fractions. Okay, so mole fraction, and I'm running out of space. Mole fraction of F2 is equal to what over what? 0.5 over 1.5. Good, it's summative, right? So what's that math? 0.333, okay? And then mole fraction of helium is equal to 1 mole over 1.5, so that's 0.66 repeat. And this is 0.33 repeat. So then, mathematically, you guys can find the mole fraction, the partial pressure by doing what? Multiplying the two. So I'm going to do 0.33 first on that space. So partial pressure of F2 is equal to 0.33 times 4.0 atmospheres. This atmosphere, you do need to put that unit there. The 0.33 again is unitless because it's a mole fraction. So what's a third of 4? 1.33 atmospheres. Or 1.33 atmospheres. You do not need a calculator for that. You can do 30-ish% of 4. Got me? Do you guys feel comfortable doing 33% of 4? Yeah. I got Alvin. I got Jacob. So what's 33% of 3 atmospheres? 1. What's 33% of 1 atmosphere? 0.3. So 1 plus 0.3 is 1.33. So just trying to support your mental math. Okay. Do you truly have to do the same exact process to find the second partial pressure? No. What could you do? You could subtract. So you could take your 4 atmospheres, subtract your partial pressure of fluorine, and then what would be your partial pressure of helium? 2.66 repeat atmospheres. Okay. Not hard, right? But new. So I just want to do at least one sample with you. All right, and you guys tell me the process on this next one. If you would like to write it down, of course, write it down. I want to talk about the process first. I'll give you a second to think. Okay, so add up what first? All the moles. Okay, so the mixture contains 4.46 moles of neon plus 0.74 moles of argon plus 2.15 moles of xenon. Can you do that in your head? Say again? 7.35 moles. And this is mental math that you could do without a calculator. So that's our moles total. Okay, and then what, Alvin? Finding the partial pressure of each gas. Okay, so I'm actually going to implement this all in one step. I'm not going to do individual steps. So can you tell me the full process first? Or I guess like the formula you could set up. What are you finding? You're finding at the end what? So let's just do partial pressure of neon first. So partial pressure of neon is equal to total pressure, which is 2 atmospheres, times the mole fraction of neon, right? So let's just set up the mole fraction of neon in one big step. Mole fraction of neon is 4.46 moles of neon over the total of 7.35 moles total, and you can do that in one step versus 2 steps. So helping you simplify your work so that you're finding ways to speed up your free response process. So we could do that in a second. Second one, what would be the only thing that changed? We're gonna have what? What would be the only thing that changed? Numerator would change, and then secondly, for the third one, the numerator would change. So if once I got the partial pressure of each 3 of these, what should they sum to? They should all sum to 2 atmospheres because that's our P total. And I'm assuming that you guys are picking up what I'm putting down. Am I okay assuming that? How about this table up here? Luke, is this table? Okay. I don't want to leave anybody in the dust, but I also know that you guys pick up things, and if you're like me, you get bored easily with some stuff that you already know. Okay. So next, I'm actually going to pause for a moment. I have some more questions I'd like to do, but before I do that, let's look at the ones that I know you all capable of doing. So look at where on the very bottom of the front sheet it says gas optional practice. What I want you guys to do first are the ones that are starred. And you're going to notice there are not only 2 questions there. If you turn to the next page, it goes through 10. Okay, so the ones that are starred and you're going to attempt right now is 4, 5, 7, and 10. And these are implementing the gas law that you showed today and that you've known from the past, but I want to see where you need to be on the introduction of gases. So start with 4, 5, 7, and 10. I mean 7, 8, and 7. Yeah. One of your parts. I'm still coming around for active reading, guys. Just leave those in your desk for me.